Hello, my name is Ryan Halstater, and I'll be talking with you today about discrete probability distributions. So first, a little bit about my background. I'm from the United States. I graduated about a year ago, where I went to Rutgers for my undergrad in industrial engineering. So basically, industrial engineering is probability and statistics with a heavy lean towards manufacturing. A lot of my friends went into jobs in that area, such as like quality assurance, and also someone into like finance with like quantitative finance personnel. I'm currently working as a software developer. I'm hoping to get into grad school for a subset of industrial engineering. So yeah, that's kind of my background. Let's go over some discrete probability distributions. So probability distributions are relevant for random variables. So we're going to go ahead and talk about those real fast first. So we have an experiment, generated an outcome. We want to map that outcome to a number we care about. It's kind of with the deal with random variables. So let's say we're flipping two coins, and for some reason we care about the number of heads that come out from those two coins. So we flipped our coin, we got tails and tails. So we're going to go ahead and say, all right, that outcome's a 0 because we got no heads. Flip it again, get 2 heads. Hey, that outcome's a 2 because we got 2 heads. So that's kind of what a random variable is, just like represents experimental outcomes by representing them as numbers. So the sample space is a set of all possible outcomes of that experiment that we're trying to represent. So here would be tails, 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 heads, heads, tails, and heads, heads, representing the ways the coins can fall. So what are some things we might want to know about the distribution of these numbers representing experimental outcomes? Hey, what's the chance you get a particular number? What's the chance you get 1 heads? If you flip 2 coins enough times, what's the long run average number of heads you're going to get? How widely varied are those numbers going to be? Are you going to get all like no heads flips, or are you going to get like a fair spread of no heads, 2 heads? Or are you going to get all 1 heads? Like, what is that distribution going to look like? How spread out is it going to be? And what is the probability of getting less than equal to 1 head flipped? So as a sidebar, something about statistics and probability is that the terminology and notation, people can use very similar notation and vocabulary to represent the same concepts. So one to be aware of is getting a value is kind of the same as realizing a value. Realizing tends to be used more in like experimental contexts, like, okay, we flipped those 2 coins and we realized a value of 1. There was 1 head realized from that experiment. So we are here to talk about discrete random variables. So what makes a random variable discrete is that the possible outcomes are discrete. So you can kind of point it and say, hey, this is it. The best way to kind of go through it is by going through examples. So the number of dots showing after rolling a die. So they're going to be 1, 2, 3, 4, 5, or 6. Like they're very clear. You can see them. They're not continuous. Like they're not on. Yeah. So we're here to talk about discrete random variables. So what makes a random variable discrete is that the possible outcomes are discrete. So discrete can be a kind of slippery term to define, but basically like you can look at it and say, hey, it's this. Like it's not really slippery. It's not like on a big range. So some examples are the number of dots showing after rolling a die. So it's going to be 1, 2, 3, 4, 5, or 6. You can kind of look at those, know what those are. A coin flipping heads or tails. 2 possible outcomes. Model a car you see driving down the street. Yeah, there's a lot of models out there, but they're finite, and you can point to and say, oh yeah, it's this one for sure. And the number of heads in 10 coin flips. Again, it can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. It's like there are discrete outcomes that you can point to. So yeah, one way of thinking about it is they can map outcomes to whole numbers. So that just can be useful mnemonic trick. So discrete versus continuous. Let's go ahead and go through some examples. So what I'm going to do is show you all the examples and then give you some time to go through them. If you want to go and pause the video, and then I'll go over if they're discrete or continuous or not. All right, so number of tires on your car. So 0, 1, 2, 3, or 4, you can't really have like half a tire, quarter of a tire. That's not like really a thing. So because of that, we're going to say that's discrete. The number of miles traveled in an hour. So You can travel no miles, you can travel 1 mile, you can also travel like 1.3758, blah, 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 blah number of miles. It's like it doesn't really map well to the natural numbers. Like it's in a range, like it can be a lot of values. So because of that, we're going to go ahead and say it's continuous. The amount of time it takes a bus to arrive, for the same reason of you can't really divide, you can't really pick out small intervals such that like, all right, it's going to arrive exactly at 0 seconds. It's going to arrive exactly at 1 second. Like there's so many of them, and it's really, really difficult to divide that we're going to call it continuous. And the number of doors in a building. So 0, 1, 2, 3, 4. Again, does it map to natural numbers? If so, it's discrete. So going on other ways to describe discrete random variables is the probability mass function, or PMF as it's frequently called. So this is basically, hey, what's the probability of getting a particular number? So there's some notation involved with this. So the probability mass function is like little f of x, which is also represented as the probability that the random variable x equals the particular value, little x. So a general notation thing, when you see a capital letter, that's normally a random variable, and a lowercase letter is normally a like actual value. So if we wanted, we could replace this with like the number 3 if we're actually evaluating a problem. So this is going to get plugged in with the number, and this is a random variable. It's like you can't replace it with a number. So given outcome, what's the probability that outcome actually happens? And every discrete random variable has its own PMF. If there's outcomes of experiments that generate numbers, there's going to be some distribution that they follow. So it's just figuring out exactly what that is. So they should always sum up to 1 because this PMF is representing literally like what's the probability of you getting a particular number. If you add up the chance of you getting all particular numbers, that is the exact same as something in your sample space happening. Like your experiment has any result. So because of that, like it's going to be a probability of 1 because something has to happen. All right, so now we're just going to show some PMFs and what they look like. So on the left, you can go ahead and see the probability of getting a heads after flipping 2 fair coins. So you can kind of eyeball it and see that the probability of getting no heads or 2 heads is both 0.25, and the probability of 1 heads is half. That adds up to 1, checks out. And for rolling a die, we can go ahead and look over, and we know that there's equal probability of getting, if you roll a die, getting any value 1 through 6. So that's reflected on our chart here, where each number has an equal probability of being selected. And also, if we were to add these up, they would add up to 1. These are kind of what they look like. All right, so next thing we want to talk about is the cumulative distribution function. So this is just the probability that our random variable takes on a value less than or equal to some number. So again, if it's all capitalized, it represents a random variable, and lowercase represents a number. So again, we can replace this with something like 1, 2, 3, like really whatever number we want. And represent this cumulative distribution function as big F of x. So as an example, if we roll a 6-sided die, what's the probability that we roll at least a 2? So the possible outcomes are 1, 2, 3, 4, 5, and 6. And we know that each outcome has equal likelihood, and there's 6 of them, and they must add up to 1. So because of that, the probability of you rolling a particular number is 1/6. Like there's a 1/6 chance you're going to roll a 4 when you roll a die. So if we want the probability that you roll at least a 2, that's the exact same as saying the probability of a 1 plus the probability of rolling a 2. So 1/6 plus 1/6, we're going to go ahead and get 1/3. And this problem is literally asking what is the cumulative distribution function evaluated at 2. So what's the chance you roll at least a 2? So now we have some graphs of the cumulative distribution function. So you can see they both end at 1 because the probability that you get less than or equal to the highest number possible is always going to be 1 because again, you have to get some outcome of your experiment. You captured all of them. So for flipping 2 coins, if we remember, our probability mass function had weights of 0.25 at 0 and 2, meaning there is a 1/4 chance of flipping 2 coins and getting either no heads or 2 heads. And there's a 1/2 chance of getting 1 heads. So because of that, we can see the probability that you get no heads is still at 1/4 because there's nothing less than that. And getting less than or equal to 1 heads is now at 3/4 because the 1/4 from getting 0 heads plus the 1/2 from getting 1 head. So for rolling a die, it's kind of similar logic where the probability of getting a 2 is the probability of 1 plus probability of 2. Probability 4 is the probability of less than or equal to a 4 rolled is the probability of 1 plus the probability of 2 plus the probability of rolling a 3 plus the probability of rolling a 4. So yeah, they scale up, and the higher your outcome number gets, in general, the higher probability of getting your random variable to realize a value less than or equal to that number also increases. So another thing to know about random variables is their expected values. So what is the long run average number you will get? If you do the experiments enough times, map them to numbers, what's the long run average you're going to get? So that's what we define expected value to be. And notation wise, we put a capital E and then some form of delineation, normally square brackets or parentheses, and then your random variable, in this case, uppercase X. So how we represent this in Mathese is kind of, we sum up each possible outcome that the random variable can take and multiply it by how likely it is to happen. So if we're going for our die example, we know that it's going to range from, that's supposed to be an I, from 1 to 6. So x, little x ranges from 1 to 6 because these are all the possible outcomes. And we know that the probability of getting the die to roll any number between 1 and 6 is going to be 1/6. So what this would look like is 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6. We're going to see a more worked out example soon, but that's the logic. It's just like, all right, how big is your number and how likely it is to happen? Let's multiply those together. Let's add them all up. Let's see what the average number you're going to get is. So in words, the sum of every possible number times the probability of that number of occurring. So let's go through an example for this concept. So let's say I'm a gambler and I say, for $1, you can roll a 6-sided die. You roll a 1 or a 2, I'll give you your money back. You roll a 6, I'll give you $3. But not like it's really $2 because you're just getting the $1 you gave me back and then you're getting 2 more. So on any other roll, I'm giving you nothing. Should you play? So that's a word problem, right? So the first thing when we're looking at this is, all right, what are they actually asking me? So should you play? Do I think I'm going to win money or lose money? If I think I'm going to win money, yeah, I'll play. I'll play as long as I'm allowed to. If I think I'm going to lose money, yeah, maybe not. That's a bad idea. So what we want is to figure out the expected value of how much money we're going to get playing this game. So where do you know for rolling a die, if we get any particular number rolled, it's with probability 1/6. So by going through the writing of our problem, we can see on a 1 or a 2, we get our dollar back. So the net change to our wealth is 0. If we roll a 6, we win $3, which is really $2. So our wealth changes +2. And on any other roll, so a 3, 4, or 5, we lose $1 because we don't get our dollar refunded. So this is great, but the outcome we care about is our change in wealth. So how can we convert this kind of like chart with each die roll's probability and the change in wealth associated to the random variable that we care about, our change in wealth? So what we can do is we can say the numbers we care about are change in the wealth, and we just got to find the probabilities of each happening. So our change of wealth is 0 if a 1 or a 2 is rolled, which in total happens with probability 1/6 plus 1/6, which is 1/3. Our wealth changes to -1 if we roll a 3 through 5 with probability 1/2, and our wealth changes to +2 if we roll a 6 with probability 1/6. So we can go ahead and throw that in a chart, right? So here's our change of wealth, and there's a probability that each change in wealth happens. So, all right, we have our changes in wealth and we have our probabilities. So I'd like to ask y'all to pause the video and try to figure out what the expected value of playing our game is from this information. What's the expected change in wealth from playing this game? All right, so to continue on, we remember our expected value formula is we're summing up for each possible outcome. What's the value of the outcome times how likely is it to happen? So here, random variable we care about is our change in wealth. So the expected change in wealth is going to be -1 times the probability of that happening. So 1/2 plus is no change in wealth. So 0 times the probability of that happening, 2/6, plus the chance of our wealth increasing 2 times the probability of that happening. If we do the math for that, we get our expected change in wealth is -1/6. So if you play the game, you should expect to lose money in the long run. So you know you probably shouldn't play this game. All right, so what are some takeaways from this exercise? So main one is figuring out what the problem is asking for. So word problems can be kind of tough. The information can be given to you in a format that's not the most helpful. For example, this example I told you, all right, for if you roll these things, you get this amount of money. That's not exactly what you cared about in the most direct format. Then you really cared about is like, all right, like what's the probability of me winning this much? What's the probability of me losing this much? So sometimes you'll have to play around with them and kind of massage your information to get it into format you want. In this case, it was, all right, what's the change in wealth and what are the probabilities of our wealth changing in these different ways? So now we're going to kind of move on to a different topic for random variables, which is variance and standard deviation. So we kind of hinted earlier, something we'd like to know is how widely varied will the numbers we get be? So like if we roll a die, like are we likely to get 3s and 4s? Are we likely to get each number like with equal probability? Is it going to be like more condensed or more spread out? So one way of representing this is variance and standard deviation. So actually two ways, but both are measures of the spread and volatility of the distribution. So with notation wise, we're going to be calling variance capital V of X and standard deviation SD of X, where again, capital X represents some random variable. So for variance, there's two main formulas. These are actually the same formula, just rewritten using some like math tricks. You don't have to know how. There's just two different formulas. Would recommend like having these easily accessible. So the variance is equal to the expected value of a random variable minus the expected value of a random variable, and that entire quantity squared. And it's also equal to the expected value of a random variable squared minus the expected value of random variable entire quantity squared. So just to highlight something, expected value of a random variable, this is going to be some number, right? It's going to be like 1, 2, 3, 4, whatever, like we can calculate it. So this is just saying the expected value of a random variable minus some random number. I don't know. Whatever, we can solve for that and square it and take the expected value of that. So we'll go through exactly how to do this in future examples. So yeah, standard deviation is literally just the square root of the variance. So if our variance is 4, our standard deviation is 2. All right, so now that we know what variance and standard deviation are, let's go ahead and go through an example. So we're rolling a 6-sided die. What's the variance and standard deviation of the number of dots we can expect to see? So we know that our expected value of the number of dots we're going to see is 3.5 dots. You can solve for this independently if you'd like as well. Would recommend it just to get practice. So our variance of the number of dots that we're going to see on our die is the expected value of the number of dots we're going to see minus the expected value of the number of dots we're going to see squared, that whole quantity squared. And we know that our expected value of X is 3.5. So we can go ahead and plug it in. So we're getting the expected value of our random variable minus 3.5, that entire quantity squared. So let's go ahead and use our friendly formula where we know E of X is equal to sum of all our outcomes times our probability density function, which is just the probability of that outcome actually being realized, happening, whatever phrasing you want to use. So when a random variable is realized to 1, this is going to be this term is going to be 1 minus 3.5 squared. So it's going to be 2.5 squared, negative 2.5 squared, times the probability that a random variable takes on the value of 1. So that's going to be 1/6. All right, and now if we plug in 2 minus 3.5 squared, negative 1.5 squared, and then times the probability of us rolling a 2, which is going to be 1/6. We just continue the logic through when we roll 3, 4, 5, and all the way to 6. we're going to go ahead and get all these terms. We're going to sum them up, and we're going to see that our variance is going to be 35 divided by 3 dots squared. So question we have at this point is, what the heck do dots squared mean? That's kind of why standard deviations are used, because variances, the units are very hard to interpret. Like a lot of times in writing, I may not even see them written out just because, like, what does that mean? But the units for standard deviation are a lot clearer, as you'll see. Because standard deviation is literally defined as the square root of the variance. So it's going to give us a number, and then the units are dots. So that's a lot easier to interpret. So kind of the intuitive interpretation of this is, the higher the variance of standard deviation, the more spread out your data are going to look. Like a low variance, your data is probably going to be very centralized around one point. High variance, it's more likely to be spread out. So to kind of draw that out, something like this probably going to be the low variance. Don't know why I hooked back. And something more spread out like this is more likely to be higher variance. Because if you grab a number, you might grab a 0 here, a 20 here, a 10 there. Like, it's just, the values you can get are going to be a lot more spread out than here, where you might get like an 8, a 10, a 12. Like, there's not going to be a huge range in values you're likely to get. So there were two formulas to variance, if you remember correctly. So there was this one, which is expected value of the quantity x minus your expected value of x squared. And there's also this formula, which is expected value of x squared minus the quantity expected value of x squared. So if we want, we can go ahead and solve for the expected value of x squared. So that's going to be, for shorthand, the probability of getting any particular roll, which is 1/6, times probability times what x squared is when you roll a 1, which is 1. X squared is when you roll a 2, which is 2 squared, which is 4. When you roll a 3, which is 3 squared, which is 9. That's where all these numbers are coming from. You do the math, you get this result. Then we get our variance is this result minus our expected value squared, which is 3.5 squared, which gives us the exact same answer as we found using the original formula. So something you might have noticed is that we can plug things into the expected value function that aren't just our like normal random variable on its own. So something we can do that's kind of interesting if we want to is we can redefine random variables. Feel free to ignore this. This is likely to be confusing, but just as this is something you are looking at, are like, wait, how can we take the expected value of random variable squared? If we want, we can define a new random variable, right? So let's say y, random variable y, and that's just equal to whatever value the random variable x takes on. Cool, square that. So then this equation is the exact same, right? So when we roll a 1, this is 1 squared, which is 1. And the probability of y taking on the value of 1 is 1/6, because it's the same probability of you rolling a 1. Likewise, if you roll a 2, 2 squared, 4. So then y is 4. The probability of y is 4 is the exact same as the probability of you rolling a 2, which is 1/6. So that's just a neat thing to think about. If that makes these formulas easier for you to work with, is you can redefine other random variables in terms of random variables, and then you can say the expected value of y is the exact same as the expected value of x squared. So yeah, again, in terms of computations, this really doesn't make a difference. This is just can be helpful if this is something you're feeling stuck on and like, wait, how can we take expected values of random variables squared or functions of random variables, such as up here. We just, if it's easier to think about, we can define a new random variable in terms of those features and then plug that into our equations. So some takeaways from our discussion about variance and standard deviation is variance should always be positive. Like negative variance just isn't a thing, it doesn't have meaning. So we're thinking of variance as a measure of how spread out your data is, where if you have a low variance, it's probably very centered around a point. And if you have high variance, your data is probably really spread out, or there's some way that outliers are more likely or something of that nature. So if we're operating under that impression, when variance is 0, no matter what happens, you're going to get the exact same value. So let's say you drop a ball and your experiment is, does the ball hit the floor? It's always going to hit the floor, like gravity is a thing. So because of that, your variance would be 0, because there's literally no variance. There's nothing else that can happen. You know the value that you're going to be realizing before you even run the experiment. So negative value, what would that mean? Like, what does a negative variance, a negative spread mean? Like, that's not a thing. So the reason this is nice is because if you're working a question and you get your answer of variance being negative, you know you messed something up, so you can go back and figure out what formula you miswrote or what like computational error you made. So it's also good for remembering this particular formula for the variance, because if you flip your terms around, if you're accidentally doing EX quantity squared minus EX squared, you're going to get a negative number and you can be, oh wow, I guess I messed that up. So that's good to know. And again, standard deviation has a lot more interpretable units, and that's its main advantage. And also, like, for some of the variance of standard deviation, you can plug them into later formulas that you're going to learn. And standard deviation is a pretty common thing to be plugged into those formulas. That can give some useful results. All right, so I'd like to go ahead and give y'all a practice problem. So someone has a pet turtle likes to race. Half the time it finishes the lap in 10 seconds, quarter of the time it finishes in 20 seconds, and the rest of the time it finishes in 25 seconds. So I'd like y'all to compute the expected time it would take the turtle to finish the lap, and then the variance and standard deviation of that time. So you'd like to go ahead and pause the video, work that out. I'm then going to show the solution, and for the method, you can refer back to the earlier slides. All right, so here's the solution. And again, remember that I guess the main sticking point could be the rest of the time thing. So you know that the probability of something happening has to be 1. So we know half the time it's going to finish in 10 seconds, a quarter is going to finish in 20 seconds. So the last remaining probability we need to have all these probabilities add up to 1 is going to be 1/4. So a quarter of the time is going to finish in 25 seconds. All right, so now we're going to move on to a slightly different example. So let's say we have 5 coins and we flip them all. So what's the probability that only one coin shows heads under this universe? So one of the formulas you can use is the probability of only one situation coming true is the number of permutations you can get the situation with, the number of ways you can get one heads, divided by the size of the sample space. How many possible outcomes of the experiment are there? So permutations is kind of the number of ways things can be ordered to give you desired outcome. So in our example here, we want one heads. So what we can do is we can have a heads on the first flip, heads on the second flip, and tails on the rest, heads on the third flip and tails on the rest, so on and so forth. So there are 5 possible permutations in our sample space of all possible flips and all possible orderings of those flips within the coins. So for the size of our sample space, we know that each coin has 2 possible outcomes, and there are 5 coins being flipped. So the number of possible outcomes are 2 to the 5th, which is 32. So we can go ahead and compute that, where we say number of permutations that give us our desired outcome, which is 5, divided by the number of top possible outcomes, the size of our sample space, number of possible permutations, whatever wording you want. Size of sample space is probably the most generalized, and that's going to give you some number. All right, so another way we can attack this problem is by looking at the number of permutations that you can get your outcome with, get one heads with, times the probability of one of those outcomes happening. In this case, one of our flipping one heads. So we know that there are 5 different permutations with which you can get one head with: the heads, tails, 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 flipping a heads in the second on the second coin, and tails everywhere else. So there's 5 of them. But what's the probability of one of them happening? So the like one specific one happening, like the probability of getting heads, tails, 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 tails specifically. So in order to get that, you need to flip a heads on the first and tails everywhere else. Probability of heads on the first is going to be 1/2, and the probability of tails on the next one's going to be 1/2. Probability of tails on the third one's going to be 1/2, so on and so forth. So the probability of the first one showing heads and the rest showing tails is going to be 1/2 to the 5th. So there's 5 of these one heads scenarios. So the probability that only one coin shows heads is the number of permutations, which is 5, times the probability of any one permutation occurring, which is 1/2 to the 5th. So 5 divided by 2 to the 5th which is the exact same formulation as we got through approach 1, where it was the number of permutations that achieve your goal divided by the size of your sample space. So different ways to attack the same problem, whatever wording is most intuitive to you, whatever explanation makes the most sense. All right, so on a different side. So we've been flipping 5 coins, so we've been talking about getting the probability of getting 1 head showing. What's the probability that we have 3 heads out of our 5 coins? So if we use either approach for this, let's use approach 2, where we're saying the probability of 3 coins showing heads is the number of permutations that you get 3 heads with times the probability of any one, like one particular of those permutations occurring, assuming all those permutations have the same likelihood of happening. So the probability of one of those permutations occurring is the probability that 3 coins show heads and 2 show tails, which is, let's just for the fun of it, say the first 3 coins show heads, the last 2 show tails. So that's going to be 1/2 to the power of 3 times 1/2 to the power of 2 to represent the 3 coins showing heads and the 2 showing tails, for a total of 1/2 to the power of 5th as the probability of heads, 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 tails, tails. All right, so that's one part of our formula down. So now we need to figure out how many permutations you can get 3 heads with. So both approaches hit this bottleneck, and we don't really have an easy way of doing this. So if we wanted to, we could go like the super painstaking way of writing out each possible outcome in our sample space and counting how many satisfy our requirements. But we can do that here. But what if we have 100 coins? That's just terrible. No one wants to do that. So mathematicians also don't want to do that. So they made a really convenient way of finding the number of permutations possible. And it's called a binomial coefficient. So the notation for this is a capital C, where n and k. So n represents the number of objects that, if we have objects that could be successes or not. Like for example, say we have a coin, flip heads or tails. We'll call heads a success. So in our example here, we're flipping 5 coins. So the number of objects that could be a success or not are 5, because each coin could be heads or tails. We're defining success to be heads. And then K represents how many objects we get that are successes. So here we want 3 of our 5 coins to come up heads, and we're defining heads as success. So another thing we also call the binomial coefficient, sometimes be called n choose K, because all right, we have 5 coins, we're choosing 5 of them, 3 of them to be successes. So if we want to go ahead and compute this out, choose K, so it's going to be 5 factorial over 3 factorial times 5 minus 3 factorial, which is going to be 2 factorial. So we know this is 5 times 4 times 3 times 2 times 1. So that's going to be 120. And that's going to be divided by 3 times 2 times 1, which is 6 times 2, which is going to give us 120 over 12, which is going to be 10. So because of this nice tool, we know that there are 10 possible permutations that will give us 3 heads and 2 tails. And again, the way to use this is if you have a definition of success and items that can be successful or not. Here it's flipping a coin, is it heads or tails? It could also be like, all right, you're watching cars go by intersection and did they run the red light or not? There's a definition of success. We say if they don't run the red light, it's a success. And you watched 100 cars go by. How many ways can that happen? So yeah, this can be used for any items, any definition of success. All right, so we kind of already went through this part, but how we would apply the binomial coefficient to our example is we know that there's 5 coins, of which we want 3 to show heads. So the number of items that can be successes are coins. There's 5 of them. The number of successes that we're looking to see are 3, because we want 3 heads. And if we do the math, we find out that there are, again, 10 permutations that result in 5 coins having 3 heads and 2 tails. So now if we want to compute the probability that 3 of our 5 coins show heads total, it's still the number of permutations divided by the size of our sample space. So that's going to be 10 divided by 2 to the 5th, which is going to give us some number. All right, so to continue with our trend of examples, let's say we have the same problem. We're still flipping 5 coins, but now the coins are rigged such that for each coin, if you flip it, there's a 2/3 chance it comes up tails. So same question, what's the probability that 3 of the 5 coins show heads? So using our normal approaches, we know that that probability is going to be equal to the probability of any particular 3 heads and 2 tails occurring times the number of possible permutations. So the probability of, let's say, heads, 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 tails, tails, just to pick a particular permutation. So that probability is going to be 1/3 chance of getting heads to the power of 3, because we need 3 heads, and then times the probability that we get 2 tails. So that's going to be 2/3 to the power of 2. And then we want to multiply the number of possible permutations. So it's going to be 5 choose 3, because there's 5 coins we're flipping, and we want 3 of them to come up heads. So if we wanted to, we could solve this, because we know that 5 choose 3 evaluates to 10, because we solved for it last slide. So it's the exact same idea of how to solve these problems. All we're doing is changing around some numbers. Just the probability of a success happening is changing. Instead of being 1/2, it's now 1/3. So can we generalize this? The answer is yes, we can, and it's called the binomial distribution. So this is a discrete probability distribution, and it's a generalization of what we just did. So the scenario is this: we have n trials, which are either successes or not. These trials, yeah, you can say yes, a success, no, it's not. Could be flipping 10 coins and the success is heads. It could be watching 5 swimming races, and if like your friend wins, it's a success. It could be 3 separate die rolls where success is rolling above a 3. It's just you have some number of trials and they're either successes or not. And to do this, obviously you need a definition of success. It's kind of arbitrary, so you can kind of make it whatever you want to make it, whatever's convenient for you. For example, the die roll example, we chose success to be rolling above a 3 because we could, and maybe it was useful for our particular problem. Right, so now we're going to go over some of the useful features about the binomial distribution. So binomial distribution is a discrete probability distribution. Because of that, it has a probability mass function, a cumulative distribution function, expected value, variance, and standard deviation. So most of the time we had those formulas from which we could compute things like our mean, variance, and standard deviation. But because it's a binomial distribution and like it's a known distribution, mathematicians and other people have already computed a lot of these useful features for you. So instead of having to go through some of the longer, less simplified formulas, you can kind of just use formulas people have figured out for you already. So to the binomial distribution probability mass function is the number of possible combinations times the probability of that event occurring, same as always. So number of possible combinations is, if you're looking for the number of successes, it's going to be the binomial coefficient, where n's your number of trials, and k is your number of successes. So your probability mass function is going to be the probability that your random variable takes on the value of lowercase k, the probability that you have k number of successes. So the probability of k number of successes occurring, like one of those particular instances. So to have that, you need k successes and n minus k failures. So what's the probability of k successes? The probability of success to the power of k. What's the probability of n minus k failures? 1 minus the probability of success, which is the exact same as the probability of a failure, because something has to happen. Your trial is either a success or a failure, to the power of the number of failures you want. So kind of for this reason, some people define q to be the probability of failure, which is just 1 minus p. So you can kind of rewrite this formula. Instead of this term, you can write q to the power of n minus k if you want to. It's just kind of useful for showing that 1 minus p is the probability of failure and kind of helping build intuition in that regard. So to go over some other cool aspects about the binomial distribution, the mean is the same thing as expected value in this context and is defined as n times p, where again, n is the number of trials. They have to be independent trials, and p is the probability of any given trial being a success. The variance is n times p times 1 minus p. So number of trials times probability of success times probability of failure. And then the standard deviation is the square root of that. All right, so now we're going to go through some examples of PMFs and CDFs for the binomial distribution, just to give some intuition for what they look like. So under this universe, we're going to go ahead and say that we're doing 6 independent trials. And when the probability of success is 1/4, the probability of 0 successes happening is somewhere between 0.15 and 0.2. And you can kind of see that our probability mass function has a lot of the mass to the left, where it's less likely to have a larger number of successes than a smaller number, which makes sense, right? Because your probability of success is not super high. So it makes sense that you're going to have more failures than successes on average. So if we look at our cumulative density function, we can see that towards the later numbers, there's not a whole lot of change between like 4 successes and 6 successes, just because like the mass added by like, because right, our cumulative density function for 4 is the cumulative density function of 3 plus the PDF at 4. Because the probability of being less than or the random variable taking on a value less than or equal to 4 is the probability the random variable takes on a value less than or equal to 3 plus the probability it takes on exactly 4. So because these masses over here are so small, there's not a ton of change in the later cumulative distribution function values. So as the p-value gets higher, once we get to p is equal to 0.5, there's a half chance of having successes. We can see that this kind of looks like what you think it would look like, right? So there's half chance of success. It makes sense that 3 is the most common number of successes, and then it kind of spreads out evenly from there. And the CDF, so it just reflects the PMF, it's just more cumulative. So we can see that it kind of follows this sort of motion where it gets its biggest jumps towards the middle number and smaller jumps towards the edge case numbers. So I'd like to ask you to pause the video and try to think about what the PMF and CDF would look like when the probability of success is 3/4 and 1 respectively. Then we're going to go ahead and show it and see how it matched up to your expectations. All right, so here we have the graphs for when the probability is 0.75, when the probability is 1. So for 0.75, success is more likely than failure. So it makes sense that a lot of the mass in the probability mass function says that, hey, you're more likely to get higher number of successes than lower number of successes. And the cumulative distribution function also follows the trend that like the later numbers are more likely, so they're going to add a lot more mass to our density function, distribution function, apologies. And when our probability of success is 1, we're always going to have 6 successes. So all the weight is going to be on 6 because we're always going to have 6 successes. And likewise, the probability of getting a value less than or equal to 5 is 0 because we're always going to have 6. Always going to be 6 successes. It's 100% likely. So now we're going to go over an example for the binomial distribution. So we've been talking a lot about this 5 coin flipping example. So let's say we have a fair coin. What's the expected number of heads that we would flip if we flip 5 coins? So we know our expected value formula is our number of trials times the probability of success. So here that would be 5 times a half because 5 coins, and there's for each coin there's a half chance of it being a success, which is defining as heads. So 2.5 heads. So what's the variance of the number of heads flipped? Again, if we were doing this without knowing it was the binomial distribution, we would have to use one of the 2 formulas we learned earlier and compute it out long ways. However, since we know it's a binomial distribution, we can just plug and chug, where we know our variance is the number of trials times the probability of success times the probability of failure. We know those numbers, we plug them in, we get a value. So to kind of highlight this again, once we knew it was the binomial distribution, this got a lot easier of a problem. Because otherwise, if we were trying to find the expected number of heads flipped in the old way, right, we would have to figure out the number of permutations which you get 1 heads, and then find the size of our sample set, divide by it, get a number, add that. So that's the probability of getting 1 head. So it'd be 1 times that number plus 2 times the probability of getting 2 heads plus 3 times the probability of getting 3 heads. That's a lot of binomial coefficients. That's a lot of numbers to run. That's a lot of math to run. As opposed to just kind of knowing that the expected value is going to be the number of trials times the probability of success. That's a huge time save. So we definitely recommend for word problems kind of, if you see repeated experiments or things that could be called trials that are defined as either success or failures, usually like binary, it's either something or it's not. that can be a big clue that you're dealing with the binomial distribution. So you can use a lot of these time-saving formulas rather than having to compute them by hand. All right, so I just wanted to include some practice problems on the binomial distribution. Again, these are ideally for y'all to work out independently. I'm going to show the solutions after I'm done talking about them. So what's the problem? So 1/3 of all 40 roads in the city crack within 5 years. So if you look at any given road, there's a 1/3 chance that it'll be cracked by the end of 5 years. So what's the probability that exactly 20 roads in the city crack within 5 years? What's exactly the probability exactly 20 of the roads in the city do not crack? And compute the expected value variance of standard deviation of the number of roads cracked in the city within 5 years. All right, I'm going to show the solution now. I would recommend trying to solve these problems before looking at the solution because it's going to spoil it for yourself and you learn by doing. So yeah, I think the main thing I want to highlight here is that the probability that 20 of the roads crack and the probability that 20 of the roads, let's say, do not crack adds up to 1. That makes sense. You want to find the probability that something doesn't happen. It's just 1 minus the probability that it does happen for like binary things where it's either one or the other. So that's the easy way to solve for things. And that's a trick that is very easy to ask questions about. All right, so for the binomial distribution, Excel and other like similar like spreadsheet softwares have really nice functions that can help you compute like the PMF and CDF for the binomial distribution. So I'm going to go ahead and just show what they look like, but these slides can give an example. I'm just going to show it in my particular software. So I don't actually have Excel, but I have LibreOffice, which is a freeware alternative. So the function that we're looking for is binom.distribution. If you start the parentheses, at least here it'll show you like what exactly each term means and what they look like. I think Excel has a similar functionality. So the number of successes in a series of trials. So let's say, same as we always done, we have 5 coins, they're fair. What's the probability that 3 of them come up heads? So we want 3 successes. We're defining successes as heads. There's 5 trials, 5 coin flips. The success probability is 1/2. And do you want it to be cumulative or not? So if we say we don't want a cumulative, this is going to give us the PMF, so the probability that our random variable takes on the value 3. If we say cumulative, it's going to use our CDF. It's going to be the probability that our random variable takes on a value less than or equal to 3. So for this, we're going to say 0 representing false. And that's going to go ahead and give us the PMF evaluated at 3. So the probability that our random variable takes on the value of 3. If we wanted to know what the CDF was at that point, we can go ahead and plug it in. So 3, 5, probability of success 1/2, and then true to represent if we want cumulative or not. And that's going to give us this number. So this is the probability that should be lowercase. Apologies, it's my software. The random variable is exactly equal to 3. This is the probability that our random variable is less than or equal to 3. So if we're logicking this out correctly, the probability that x is less than or equal to 3 should be the probability x is equal to 3 plus the probability x is less than or equal to 2. So let's go ahead and check it out, right? So binomial distribution. If y'all want to pause and try it home to figure out what formula to plug in here, that would likely be good practice as well. All right, so to continue on, we want the number of successes. We want 5 successes and 2 successes, pardon me, in 5 trials, where the success probability is 1/2 because it's a fair coin, and the probability of getting heads is 1/2. And we want it to be cumulative, so we're going to say 1. I think in Excel, you might have to say true. That should do the same thing. So this is exactly what we expected, because the probability that our random variable evaluates to 3 plus the probability our random variable evaluates to less than or equal to 2 is the exact same as the probability our random variable evaluates to less than or equal to 3. So yeah, these are the Excel formulas. I'll go ahead and put the slide back up. But yeah, basically the only difference between the CDF and the PMF in Excel is if you put false or true at the end. True meaning it's cumulative, and false meaning it's just the PMF. All right, so now we're going to start going into kind of review, closing out sort of thing. So probability distributions, they're attached to random variables, and they're just a way of representing like what this outcomes look like, the probability of having a certain outcome occur, like very similar to a PMF. So the reason they're useful is, for example, the binomial distribution, right? Once we identified that like a coin flipping problem or like any sort of problem fits in the binomial distribution mold, then we automatically have really easy formulas for the expected value, variance, standard deviation, PMF, CDF, a lot of useful things that otherwise would require a lot of analytical work and like thinking about it and consulting other resources. So it really helps you save time. Again, for the binomial distribution in particular, if you have a number of independent trials and they can either be successes or not, that should cue you in that you should use the binomial. Another common example is if you're pulling balls from an urn with replacement. So you have like a vase or something, there's 10 red balls and 3 blue balls. And you draw 4 balls with replacement. What's the probability that all 4 of those balls are red? So that's, you can think of that as 4 independent trials where the probability of each ball being red is 10 over 13 because because there's 10 red balls and you can draw 13 balls total in each trial. So you'd want to find the probability mass function where you get all 4 successes. So you can go in and plug in our formulas and find out that answer. But the main key is once you recognize a word problem does follow the binomial distribution or some other distribution you can use equations that are known for that distribution to solve for useful things like the expected value and variance instead of having to use those rather complicated or not complicated, but like formulas that can take you a long time to solve otherwise.